So the next paper I'd like to talk about today is entitled Robust Quantum Memory in a Trapped Ion Quantum Network Node. This is a paper from the University of Oxford using trapped ions as quantum memories for quantum networks. Some of the challenges that are attacked in this paper are creation of a reliable and long-lived memory and error correction and high-fidelity quantum gates. So just to sum up this paper kind of briefly, they are using strontium ions to produce ion-photon entanglement, and then they are transferring their entanglement from the strontium ion to a longer-lived storage qubit calcium ion, and then they're later performing some noise reduction techniques on this calcium ion in order to extend the lifetime of the quantum memory and reduce noise. So ultimately, integration of different types of quantum memories, whether it be different types of ions or other platforms as well, will be crucial to building successful quantum networks. So it's great to see that in this paper. And also performing quantum gates and quantum logic on quantum memories is also crucial for second and third generation quantum networks, and the work in this paper is also highlighting that functionality. So looking at one of the figures from this paper, on the left, part A, we can see a circuit diagram of basically the swap protocol that's happening between the strontium and calcium ions. So a typical swap gate is a little bit different from this. This is an improved swap gate, which can swap the states while introducing fewer errors. And in particular, they're able to do this swap with a process fidelity of only 0.91, and with additional error correction, they're able to improve that fidelity to 0.98. So it's a high fidelity swap. And on the right, we can see a Troy matrix of their iSWAP circuit, which they've measured from their experiments, and a Troy matrix just being one way of representing the action of a quantum channel. The process fidelity and error correction fidelity can also be extracted from this. So the next figure I'd like to highlight from this paper is showing the ion-photon entanglement fidelity of ions in their of the strontium calcium ions that they're using against basically storage time. So initially they have entangled their photon with a strontium ion, and they're able to produce this entanglement at a fidelity as high as 0.97, but the strontium ion has a relatively short coherence time, so this fidelity drops right away, and that's this purple line. When they perform a swap to swap their entanglement from the photon strontium pair to be photon calcium, they initially have a bit of a hit to their fidelity down to 0.93, but their coherence time is increased a lot, as we can see from the orange line, and from the x-axis, which is log. And then finally, with even with this orange line, though, there's still is magnetic field noise and noise from the ions being in a laser interaction region, which is affecting the coherence time and fidelity for the quantum state. So when they transport the ions away from the laser interaction region and also implement dynamical decoupling, in this dark red line on the right, they're able to see quite nice coherence times of even 10 seconds with fidelities of about 0.8. So to sum up this paper, it's a really great paper showing how trapped ions can be used as quantum memories in quantum networks, and how noise reduction techniques can be used to extend their lifetimes, as well as showing implementation of a iSWAP gate as well.